Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Next speaker, Rich Caruana. So Rich Caruana is a senior researcher at Microsoft Research, and his research focus is actually quite varied and wide. He's been working and is interested in learning for medical decision-making, deep learning, adaptive clustering, computational ecology, and actually prior to Microsoft also what he's been doing has been also quite diverse. He did his studies at Carnegie Mellon in the Center for Learning and Discovery, also worked at Cornell University and UCLA at the medical school. And today he's going to tell us how deep nets need to be. Rich.
Hey, is the mic working? Good. So I'm Rich Caruana, Microsoft Research, and I'm going to tell you about some work we've been doing on trying to better understand why deep learning, deep neural nets works. And this is work that started last year with an intern from University of Toronto named Jimmy Ba. Okay, so here's 3 different kinds of neural nets. These are the sort of shallow neural nets that all of us trained 25 years ago in the early 90s. We have inputs, a nonlinear hidden layer, typically 1 or at most 2 layers, and then the outputs, and we train it with vanilla backprop. This is a deeper neural net in the middle here. This neural net has 3 hidden layers between the inputs and the outputs. These are typically nonlinear units like sigmoids, just conventional stuff. It's really just this model with extra layers in it. And then you might use some extra tricks when you train this layers. You might do some sort of pre-training, or maybe you're going to do some sort of regularization like dropout. But this is a deep neural net. And I guess I consider sort of 3 nonlinear hidden layers to be the sort of smallest neural net that deserves to be called deep. Then this is a more complicated deep neural net on the far right here. This also has 3 nonlinear hidden layers, but before that, between those hidden layers and the inputs, there's these convolutional layers. So in convolutional neural nets is something that was created in the late 80s, and it's still something that's very powerful. And I'm not going to go into what they do. Most of you are probably familiar with them, but basically they make it so that instead of having to learn to recognize a face or a feature of a face in one region and then having to separately learn how to do that for every other region, say the upper left-hand corner of the image, instead we can build one feature detector to learn some piece of a face, and we can map that, scan it around the entire image. And that's effectively what convolution gives you, at least in images. So these are shallow neural nets. This is a moderately deep neural net, and then this is an even deeper neural net. Now, I'm going to show you some results on the Timid speech recognition data set. Timid is Texas Instruments MIT data set. It's been around 20 plus years. It's been around a long time, so many people have worked on this data set and tried to get good results on it. This is a picture of what Timid data looks like. This is time on the x-axis, and these are frequency bands on the vertical axis. And basically, this is a speech utterance. I'm told that people who work in this all the time can actually recognize what you're saying by looking at these pictures. I cannot do that. We turn this into features, and what we end up with is an input vector that's about 1,800 input features, and then there's 183 triphones that we're trying to predict from this data. And on this particular data set, this would have been considered a very large data set for the early 90s. We had about 1 million frames in the training set. There's about 450 speakers in the training set, another 50 speakers in a development set, and then finally 24 speakers in a test set. So this is considered a fairly large data set. And that's one of the reasons why people have been able to use this data set with deep learning. So now let me show you some results. So as I said, this data set's been around a long time. These are error rates. So this is a 25% error rate. And this is back in 98. This is about the best people could achieve after a decade of working on this data set. So this was considered extremely good performance circa 1998. It took a tremendous amount of effort to develop the models that exhibited that kind of performance. So this was really good stuff. And then what happened is nothing. people continued to work on the data set and very little progress was made. That is, it was very hard to do better than this Bayesian hidden Markov model. And these numbers basically stood for about a decade. So people did not make much progress. And then deep learning happened. So the first attempt combined deep learning with a hidden Markov model in '09, and suddenly a sort of 2% reduction in error rate. So that's really significant. When people haven't been able to move this number for a long, long time, suddenly you see a 2% reduction. Then people tried a variation on this, adding dropout, a regularization procedure, a huge additional improvement, another 3% improvement in the error rate. Then people tried convolutional nets, another kind of deep neural nets, yet another % improvement. And the rumor I've heard is that maybe it's Jeff Hinton has a recurrent neural net that is now doing incredibly well. And if you look at this, realize this is the result of a decade of work, and then this number stood for a long, long time. And all of a sudden, as people start applying deep learning to this problem, there are dramatic reductions in the error of these models. This is really tremendous, tremendous improvements. So let's talk about that. So, you know, why is it that if we take a humble neural net like this, which is kind of shallow, and add a few more layers to it, and do a few extra things, that all of a sudden we start achieving accuracies that were undreamt of before we did that? So why is that working? Well, there's a number of possibilities. So one possibility is that you get from these deep models some sort of extra expressiveness in the functions that you can express and learn, but you get that without requiring some exponential, say, increase in the number of parameters. So this is one argument for why deep learning works. And this is true for certain classes of functions. Certainly it's true for parity functions, that a deeper model is actually more expressive in that class than a shallow model with more parameters. Another possibility is that these sort of feature hierarchies that get learned in the deep models is really critical to learning well from limited data. So in image processing, when people look at what's learned in different layers, they sometimes see that we learn sort of edge detectors, SIFT-like features in the first layers. Then we start learning things that, you know, if this is a face recognition problem, we might start learning pieces of faces in sort of middle layers. And then in final layers, we actually start combining those pieces and learning things that are like faces. Maybe it turns out that learning a hierarchy of features is just critical to getting good performance on the kind of tasks that we're applying deep learning to. It's possible they're working just because the learning algorithms we have right now are just very well suited to these deep models. So it may have nothing to do with this hierarchy of features or with the expressiveness of the model class. It may just be that our current learning algorithms and regularization methods, such as dropout, are just very well tuned to deep learning. Now, it could be that it's some combination of all of these effects. It's possible that it's none of these effects. You can actually come up with additional reasons why these things might work. So what we're going to do is try to look into this a little bit and try to figure out a small piece of what might be going on here. So now, many of you will know, if you know the history of neural nets, that we had representation theorems from the 90s, which basically said that a single layer neural net with nonlinear units, if you put enough hidden units there, is capable of representing any reasonable function. So we're not talking about, you know, we know that a single hidden layer could do it. It's just that we observe empirically it doesn't do it. So we're really more interested. This is really a representation theorem. It says if you were to make that layer big enough, there exists a neural net which would represent the function that you're interested in. But we observe that when we make those layers big enough, we don't learn that function. So it's important to realize that these representation theorems are theories of what's representable, not theories of what's learnable from data. And we're much more interested in, given the kinds of functions that we need to learn, given that we're learning from real data, often limited real data, do the deep nets really have an advantage? They seem to have a big advantage. Do they really have a big advantage over shallow nets? So that's what we're going to talk about. Okay, so let me show you what our new results are. This is a summary of where we're going. So remember, these are the error rates. This is a shallow neural net with one hidden layer. When we train it, we get error rates of about 23, 24%. If we make it 3 hidden layers, we reduce the error rate about 2%. So this mirrors the results that I showed you in the other table. If we make this a convolutional model, this is Li Deng's convolutional model, we drop error rate another 2%, so this is a very big reduction in error. And then what I'm going to show you is that we've been able to train shallow neural nets If we make the number of parameters small so that it's like this, we're able to train a shallow neural net that has comparable accuracy to this, even though it has only one hidden layer. And if we make the number of parameters in that shallow neural net larger, we're able to make that neural net as accurate as this convolutional neural net, even though it has no convolution in it. So I'm going to show you how we do that. OK, so I'm going to just describe 3 of the tricks that we use to make that happen. One is a model compression. Another is a trick for speeding up learning. And then the final one is this ensemble of convolutional neural nets. Let's talk about model compression first. Actually, we'll spend most of the time talking about that. So it's very, very simple. This idea has been around about 10 years. What you're going to do is you train some massive, very smart model. Then you pass a bunch of unlabeled data. Then you pass some huge amount of unlabeled data through that very smart model, and you collect the predictions that that very smart model makes. And then we're going to train another model, often a smaller model, on this synthetic data set to mimic, to learn the function that was learned by that very smart, probably very big model. So we're doing, quote, a compression trick because we're trying to get a small model to learn the function that was learned by a bigger model. So that's the game we're going to play. It's very simple. Let me show you, this is a result from almost 10 years ago. So this is root mean squared error. So down is good. Squared error of 0 would be down here. This is a neural net that was trained on this original data set. It's the best neural net we could train, trying many different architectures, many different training procedures on the original data set. It has a squared error just above 0.1. It's a pretty good model. But we were able to train a better model with this ensemble selection technique that I'm not going to talk about. But this is a much smarter model than this neural net. And then we did this trick, this compression trick, which is we took a bunch of unlabeled data, passed it through this very smart model, collected its predictions, and then we trained neural nets of different size. This is number of hidden units of this mimic model on the x-axis. We trained neural nets of different size on this synthetic data collected from the very smart model, and it's trying to mimic this model. And you can see that by the time we get to, say, 32 or 64 hidden units, this small neural net, in this case with one hidden layer, is able to yield an accuracy almost as good as the model that's teaching it, that's being used to label its training set. And the remarkable thing is not necessarily that the neural net was capable of reproducing this ensemble. The amazing thing is that we couldn't train a neural net on the original training data to do that in the first place. That somehow by going through this smart model as an intermediary, using it to label data, and then training a neural net on that synthetic data to mimic this model, we're able to achieve better accuracy. So that's the game we're going to play. Why did that work? Let me just give you some quick reasons why it might work. This is a very intuitive description. If there were some errors in the original labels of the data, if the smart model didn't make those errors, didn't overfit to the data, those errors are now gone from the data that's being used for the mimic model. So that's an advantage. Similar to errors, maybe there's just some labels that are incredibly hard to learn. They're in sparse regions of the space where things are very complicated. It may turn out that the smart model basically didn't learn to do this complex function approximation in that region of the space, so it presents a simplified, smoother version of the function for the mimic model in that region of the space. Also, the function that the mimic is trying to learn is learning friendly because it was already learned by another learning method, right? So in particular, while the original data, the labels may depend on features that were not available to the learning method as inputs, at this point, once we're trying to learn the function that was learned by this other model, it is just a function of the inputs. So any dependence on features that were not available has been washed away by going through this intermediate model. That means, again, the mimic model, the student model, has an easier learning problem. So finally, we're going to use soft targets. So often the initial data is 0, 1 Boolean labels. That can be hard to learn from. Instead, we're going to use soft values like probabilities, 0.2s, 0.9s, 0.7s. And we're going to do soft learning here. And that also seems to make the mimic model easier to learn. OK, so here's the objective function. So instead of doing the usual softmax 0, 1 log loss kind of training that you do on 0, 1 targets, instead we're going to take the probabilities before they go through the softmax that the smart model has predicted, and we're going to learn those probabilities with the mimic model using squared error. Okay, and this is just a simpler objective function. in many cases for learning. Now, we don't, on Timid, actually have any extra unlabeled data. So what we're going to do is we're just going to take the training set and we're going to throw away all the labels. After we train the really smart models, we'll just throw away all the labels and we'll reuse that as our unlabeled data and make predictions with it with the smart model. And this is a hard way to do compression. You'd actually like to have lots of unlabeled data, which we don't have. So we're going to use some trickery to sort of overcome the loss of accuracy that typically happens when you do this. OK, so let me show you the results on Timid. This is really going to be the heart of the talk now, is the next few slides. OK, so let me show you this graph. So here we have accuracy on the Timid development set. So up is good. This is the number of parameters on a log scale in millions that are in the model that we're training. So these are pretty small neural nets over here. And this line is for a shallow neural net, just one hidden layer. Okay? This is pretty small networks over here. These just have 5, 10, 100 hidden units in it. By the time you get in here, 1 to 10 million parameters, these are pretty good-sized neural nets. These have somewhere between 1,000 and 10,000 hidden units here. So these are getting to be pretty big. And then these are pretty big neural nets. So these neural nets are starting to have 200,000, 400,000 hidden units. And in fact, that neural net is just the largest single hidden layer neural net we could train on our GPU. So that's why the graph stops there. Now let's look at the graph. So what do we see? Remember, this is just a shallow neural net. So there's no deep learning here. There's no mimicry. This is a shallow neural net being trained on the original data set. So this is how well you do. Well, if the net is too small, you don't do too well. We've known for a long time that having a lot of extra capacity in neural nets seems to help. We sort of do well when we start getting to maybe 10,000 hidden units in this shallow neural net. And our accuracy peaks at about 78%. And then maybe there's even a sign that we start overfitting if we go beyond that. OK, that's a shallow neural net. If we had the horsepower, we could have trained this neural net back in 1990. So there's nothing unusual happening there. This is a deep net. This is 3 hidden layers, no convolution, just 3 hidden layers. Deep net being trained on that same data. And again, we're counting the number of parameters here. So the deep nets that are around here are sort of 2K by 2K by 2K. That's how they have a similar number of parameters to something that might be 8K or 10K hidden units if it's a shallow net. And what do we see? Well, nobody does very well out here when the models are too small. Once we get to models that are large enough, the deep nets do significantly better, 2% better than the shallow nets, right? So this is the magic of deep learning. This is something we didn't know about until the last 5 to 10 years. OK, so this is great. And then performance levels off. Once we get to a network that's about this size, which I think that might be the 2K, 2K, 2K model, basically there's no extra advantage to making it bigger. Here's a convolutional deep net. So this is Li Deng's model. So this is this blue line. This is a convolutional layer, max pooling layer, then followed by 3 nonlinear layers, as in that model. And I haven't done this versus the number of parameters. We haven't actually run the expensive experiment to let us vary the number of parameters. Plus, it's not really clear how to vary the number of parameters, right? We could change the convolutional layers so that they were different. We could change the number of parameters in the first nonlinear layer that's attached to the convolutional layer, vary the number of parameters afterwards. It's actually more difficult to know how to vary number of parameters in a convolutional model. So we haven't done those experiments. Instead, it's just a sort of target that we're hoping to reach, right? This is already a deep model. This is a deeper model. And this is great, right? Again, we're seeing a sort of 2% increase in accuracy by adding convolution, making this model deeper. Now I'm going to show you another line, this purple line, where we've got yet another % increase. And what we've done is we made an ensemble of 9 of these convolutional deep nets. So this is really state-of-the-art performance. I mean, this is very good performance. This is sort of excellent performance, and that's sort of now state-of-the-art performance. That's performance that's hard to achieve. Very few models. Maybe the recurrent neural net is the only other model we know of that achieves that kind of performance. So that's an extremely high-quality model. And now what I'm going to do is I'm going to train a shallow model. So it's like this red curve. But I'm going to train the shallow model on the targets that come from that really smart model. So again, I'm going to take the training set, throw away all the original labels. I'm going to label the training set with that model, that ensemble. And then we're going to train a shallow model just like this, but we're going to train it to mimic that model. This is sort of remarkable. So let me show you what's happening. Again, nothing is doing very well when the models are too small. In fact, this model doesn't do very well at all when it's small. Two interesting regimes here. One is in this middle area where the deep neural net with 3 hidden layers is starting to level off. This model, remember this is number of parameters in the model, this model for a similar number of parameters is doing just as well as the deep neural net. Right? So here we have a shallow neural net with the same number of parameters as a deep neural net doing just as well or even a little better than that deep neural net. Now it had what I would call an easier learning problem, which was it didn't have to train on the original training set like this model. It got to train on this synthetic data set that came from that model. It's interesting that this model presumably makes more errors in the training set than the original labels did. But somehow it's still an easier to learn function. And that easy to learn function is better learned even by a shallow model. So this is very interesting. It means that for the same number of parameters, we're basically matching a deep net in this regime. If we go further and we're willing to increase the number of parameters in this shallow mimic model, it does even better than the deep model. Even if you had given the deep model lots of extra parameters, it doesn't know how to use them. This shallow model is able to do as well, in fact, as the convolutional model. And the amazing thing is that the shallow model has no convolution in it. It really is just a fully connected feed-forward shallow model. So this is just remarkable. And if you remember anything from the talk, I think this is the slide to remember. OK, so let's just go through that a little bit. We get exactly the same results. That was the dev set I was showing you. We get very similar results for the test set. So there's no overfitting happening here that's making it happen. We get exactly the same results no matter how we run the experiments. So let me just show you some things that we've learned. One is the fact that we're training to squared error when we do the mimic model means that we're much less prone to overfitting than if we were training to the original 0-1 targets with log loss. And I won't go into this any detail because we don't have much time, but basically we found it's almost impossible to overfit these shallow mimic models. And in fact, we did everything we could to make them learn faster, as I'll show you in a second. So they're very immune to overfitting. So we don't even have to use dropout or any of the regularization techniques that you would normally use. So that's a surprise to us. I'll skip that because I've already said it. Let me tell you about this speed up trick that we had to use. So this is a shallow neural net, right? Here's the inputs, the nonlinear layer, and then the output layer. What we had to do, it's so resistant to overfitting and so slow to learn that what we had to do was put a linear layer between the input units and the nonlinear layer to act as a sort of linear, easily learned bottleneck layer. And we did this. It turns out it actually hurts the accuracy of this model. This model is slightly more accurate than this model. The beauty of this model, though, is it trains almost 10 times faster than this model. So this is not a trick that we're doing in order to improve accuracy. We'd actually have higher accuracy without it. But we are doing it to speed up learning. It turns out it's very important for that. And then the interesting thing is because this is a linear layer, you can just absorb the weights of this linear layer into the weights that are already going to the nonlinear layer. You can afterwards get rid of this. You can compile it into the rest of the network if you want. So, and I think I'll just skip, and I'll skip. And then I'll show you this ensembles trick. So basically, we're able to train a teacher net of different kinds of accuracy depending on how we train the teacher net. We could make the teacher net be just a 3-layer deep neural net. We could make it be a convolutional 3-layer deep neural net, or we could do an ensemble of convolutional neural nets. And every time we did that, the teacher got smarter. And it turns out if we would train a student to mimic these models, every time we made the teacher smarter, the student would get smarter as well. So we didn't see any evidence that the student is sort of lagging behind in its capacity or ability to learn what has been learned by the smarter teacher model. So that's an interesting result. And that's why we went to the ensembles. The reason why we have this large gap is because we don't have any unlabeled data in this domain. If we had 10 million or 100 million unlabeled examples, we could close this gap and force the student to learn essentially the same function as the teacher. But because we don't have the unlabeled data, we're not able to do that. So the way we played the trick of making this model very smart was by making the teacher very smart, by making ensembles. So that's one of the tricks we had to play. So it looks like if you squint, maybe deep nets don't really need to be that deep. That is, it is possible that a shallow model with a similar number of parameters could actually learn these functions that are being learned by the deep models and learn it, not just represent it, but actually learn it. So that's really exciting. Maybe that's just true for Timid, though. So let me just give you a peek at some more recent results that we have on CFAR 10, one of the image recognition problems. So these, again, are error rates. And if you take a pretty shallow neural net, a 2-layer shallow neural net, you get pretty high error rate. This is a 10-class problem, so getting an error rate of 50% is not too surprising. So this is a very hard learning problem. This is not a very good model. If we take that shallow neural net, we make it very large, we do some pre-training to it, and then we add dropout as a trick for regularization, we do get some, this is basically, we start doing deep learning kinds of things. We do get a dramatic reduction in the error, so that's great. Now, if we go all the way to a full-blown convolutional model, that is 3 layers of convolution and max pooling, followed by 3 nonlinear layers, then we get a dramatic further improvement in the accuracy of those models. And what we've been able to do is train shallow models, just like we did before, to mimic an ensemble of these guys. And depending on the size of these shallow models, we're able to get either the same accuracy as this deep convolutional model or slightly better than it. And I should say that this shallow model, we had no convolution in the shallow model for Timid. We did find that we had to add a single convolutional layer when we were trying to mimic these models. So we don't have 3 convolutional layers, we have a single convolutional layer. But it turned out that at least 1 layer of convolution, then followed by 1 nonlinear layer, was important for getting those kinds of results. Okay, so it sort of suggests we can play exactly the same game on a domain other than speech recognition, other than Timid. This is image recognition, and get very similar results. So what's a summary? It kind of works. Shallow models are, in some cases, capable of learning similarly accurate functions as these deep models. And in fact, if we make the shallow model very large, it's capable of learning from not any extra data the same kind of models that we could get with these complex convolutional models. It's the ugliest algorithm in the world, right? The first thing we do is we go ahead and we train the deep complex model. We train lots of them, make an ensemble of them, pass a bunch of data through it, and then we train a small model to mimic that model. So it's not something that we consider to be an attractive algorithm. It's more to just give you an existence proof that it is possible to learn shallow functions that have this kind of accuracy. They don't really have to be deep functions. The ensembles themselves are great. They represent a new high watermark on some of these problems. And then we're getting some mileage out of using these sorts of tricks to train, let's say, smaller models to mimic very accurate, much larger models, so that these smaller models can be run, say, on your smartphone or on servers at real speed. So, and I just want to thank some people, including Li Deng, who's in the audience. And let me just stop there. Thank you.
Thank you. So we have time for one question. I guess we have a panel here. So just while the mic goes there.
Oh, sorry.
Sorry. While the mic.
Oh, I thought it was there. Yeah, so with your conclusion when you said that they don't need to be deep. However, you do use the output from the deep model to train as the alternative target to train the shallow model. And in that sense, you cannot just, conclude that you don't need to. They don't need to be deep, right?
Right now, we have no idea how to train a shallow model to be this accurate from the original training set. We have no idea how to do that. So you're correct that the only way we know how to do that is to go through these deep intermediate models, collect their predictions, and then train the mimic to mimic those deep models. It's the only way we know how to do it. And Yoshua Bengio makes the argument that, well, maybe the inductive bias of these deep models is just better for our current learning algorithms and our current data sets, and it's just easier for them to learn the right function. And then somehow this compression trick makes it sort of not too difficult for us to push that function into a shallower model. Yeah, but you're exactly right. Right.
Question.
Right. But I guess I believe there's at least a 50% chance that there exists a learning algorithm which could train the shallow model from the original training set without going through the deep intermediate. 50% chance. So that's.
Hi, Ankur Teredesai, University of Washington, Tacoma. There is a lot of work that happened in the early 2000s on evolving neural networks with genetic algorithms or so on. So has anybody looked at deep versus shallow neural networks and compared them with neuroevolution?
So, and there's even work that goes back further. Scott Fahlman's work on cascade correlation in C2 nets, which also grows a sort of wide, deep model starting from something small and grows it bigger. My understanding is that neither of these methods are capable of duplicating what is currently being learned by these deep models, that you have to go to the quote, new deep model technology to get these kinds of accuracies. And we're just showing that, at least in principle, it's possible for a shallower model to learn similar functions.
Okay, last question as we transition.
So in an early slide, you had this visualization of what the layers actually represent. Right. For these new, very shallow nets, do you have some kind of visualization of what they mean, what that means?
It's a great question. So on the speech recognition, of course, it's very difficult to do visualization. So that's one of the reasons why we're pushing now on the CFAR10 problem, in a hope that we'll better understand how the shallow model is mimicking the deep model, whether it's learning different units that would map to different layers of the deep model, or whether it's learning some completely different way. It's a great question. It's what we're looking at next. Yeah. Okay.
All right, sorry. Last question.
So in some sense, you're doing regression in the last stage when you're learning a different target function, right?
Doing what?
Regression.
Yes, it absolutely
right?
is regression.
Now, suppose instead of using a shallow network, you can use deep neural network for regression. What happened?
So it's a very good question. I mean, you'd like to think that some of what we're doing can actually make the deep neural nets themselves better. And it is possible to train deep neural nets with regression, but we don't know any trick right now. See, the mimicry process, if it works incredibly well, it means that the student is exactly equivalent to the teacher. So there's not a sort of bootstrapping method here that would necessarily let the student sort of jump ahead of the teacher. It doesn't mean we haven't tried, and it is occasionally, you observe that the student is actually better than the teacher, but not by much. But
your learning vector is not as good originally, but now you have a better target that you can predict. So you can actually still go back to deep
right.
network, maybe you'll do better.
Right, so we have tried train the deep model the usual way, then replace all the targets with the predictions of a deep model, and then train another deep model with regression to mimic that model. And we never achieve accuracies that are better than the original deep model. Yeah. We don't know how to do better deep learning using these tricks yet, but we are trying. So.
All right, fascinating. I'm sure you'll get more question and interactions at the break. Let's thank our speaker again. Our last speaker of the session is Isabelle Guyon. She's the president of ShaLearn, which is a non-profit organization which is dedicated to organizing challenges. She's also the vice president of the UniPenn Foundation and adjunct professor at New York University. Her expertise and her areas of interest are in specialized is a statistical data analysis, pattern recognition, machine learning. And prior to that, Isabelle Guyon was a researcher at AT&T Bell Labs, and she pioneered some applications in the area of neural networks and is one of the co-inventors of SVMs. Isabelle.
Thank you, Evelyn. So thank you very much for inviting me and giving me this opportunity today to talk to you about some of the results of the challenges that we've been organizing. So after doing research in machine learning for a number of years, I started doing another way of performing research, crowdsourcing research. That is, instead of performing research myself, I put out problems and I let other smart people solve them. So I found that an amazing way of contributing to making machine learning solve hard problems out there in data science. And today I would like to share with you the results of a challenge I organized in causal discovery. After organizing many challenges in machine learning and particularly in causality, most of which delivering either non-conclusive results or negative results, we finally, in 2013, organized a challenge which delivered amazing results. So I'm very excited to share that with you today. And we keep organizing challenges. One of them I won't be talking about, but I will be talking about today this challenge in cause-effect pairs, of which we'll run a remake this year on the Microsoft Codalab platform, which is a platform that has been developed in collaboration with Microsoft and Stanford University that Evelyn has been the head of the development. And thanks to her, we've been able to make even bigger difference in this field. I would like first to acknowledge the many people who contributed to that effort, and starting with the people who give the impulse to the project by pointing out the problem to my attention. Some people at the Max Planck Institute, Joris Monge, Dominic Jansing, and Bernard Schalkopf. And many people who contributed the early algorithms on the problem and who made their code available, and that was a great stimulation to the challenge participants. And I would like to thank also very much the people who helped collecting data and putting out the problem on the website, and the people who tested the protocol of the challenge. And finally, I would like to thank also the sponsors who made this research possible, and particularly Microsoft, who's been very supportive of our challenges over the year and who are continuing to support our effort. Another key type of actors in challenges are the participants themselves. And we have hundreds of people who are donating their time to solve these hard problems. And they've been truly amazing because the prizes are only a tiny little motivation. They're looking to solve interesting new problems, to learn. Some people are just working during the daytime and spending some time at night trying to solve these hard problems. So what affects your health, the economy, climate changes, etc., and which actions will have beneficial effects? Those are some of the central questions that affect our well-being and our happiness. And wouldn't it be nice, if we had a means of mining existing data sets and finding potential answers to those questions? The scientific method proceeds as observing first correlations between pairs of variables, then hypothesizing causal relationships. Does A cause B, or B cause A, or are A and B the consequence of a common cause? And then perform experiments to put these hypotheses to a test. However, experiments are generally costly. They can be unethical, they can be impractical, or even infeasible. So it's really important to prioritize them. That is, to find those candidate cause-effect pairs that have the highest priority for us to experiment with. You keep hearing, in the news all sorts of causal claims. So this is these are results that have been extracted from a recent paper published in the New England Journal of Medicine that found high correlation between chocolate consumption and the number of Nobel Prize per capita. Shortly thereafter, on the internet, there were some claims that eating chocolate produced Nobel Prize winners. But if you look a little bit longer on the internet, you find other claims, like geniuses are more likely to eat lots of chocolate. Obviously, either claim could be correct, and correlation doesn't mean causation. But our objective is to take lots of such correlation found in big data, but go beyond the simple idea of correlation and rank those pairs of variables in order of alleged causal relationship, having at the top those causal relationships that are most likely to be valid. and then putting them to a test like we did before, and finally take action. So the second step is what we are focusing on. Formally, the problem consists in taking pairs of variables. So say A is the chocolate consumption, and B is the number of Nobel Prizes per capita. And we get samples from these variables. So this may be amazing to you that we're talking of the causality and we are throwing away the time component. But think of that as a cross-sectional study in the medical domain, where you're taking a population of patients and you're measuring, for example, whether patients are smoking or not, and whether patients develop lung cancer. So in a cross-sectional study, you're not taking time into account. So each sample here, in the case of chocolate consumption and number of Nobel Prize per capita, was a country. In the case of a medical study, each point here would be a patient. And we can plot each data point in a scatter plot. And the question is whether looking at the scatter plots, you can determine whether A is a function of B, B a function of A, or neither. And it is in that sense that we define causality. Is one variable a function of the other variable? And we formulated the problem as a classification problem. One class is the A cos B. So B is a function of A and maybe some other variable. And the other class is everything else. So A and B are independent. A and B are caused by a third variable that is a latent variable unknown to us. Or B is a cause of A. And because of the symmetry of the problem, of course, you could consider separating B causes A from everything else. So in the end, what we ask the participants to do is to create what we call a coefficient of causation, a coefficient which is large positive for A causes B, small negative for B causes A, and near zero for all the other cases. And using that coefficient of causation, you can set a threshold on that coefficient and then classify the scatter plots in A causes B versus everything else. Or if you set a different threshold, you can classify in B causes A versus everything else. So by bringing that back to classification problems, we can use the usual metrics like area under the ROC curve to measure accuracy of classification. And here we actually average 2 AUCs, one for the problem of A causes B versus everything else, and one for the problem of B causes A versus everything else. So the scores I will be reporting in the rest of my talk are always in AUC. So these are scores that are for the best values is 1, and random guesses is 0.5. So one solution, I shouldn't say the solution, one solution to the problem is to put it out in the form of a challenge and to have a lot of participants try to solve this. And on that graph, I'm showing you that moving from random guess to using plain correlation or even fancier independence tests doesn't bring you a lot of performance improvements. The baseline methods before we started the challenge were around 0.6. And during the challenge, we got this big leap in performance. 267 participants entered. And at the end of the challenge, we had performance above 0.8. And that is truly amazing, at least to us. It's the first time in all these years we've been organizing challenges that we had a really, really, really big improvement compared to baseline methods. And I'm glad that Rich Caruana gave a talk before, because I feel less embarrassed to present a method that is very heuristic and that's kind of a dirty solution. The participants came up, with this big leap in performance, but their solution's kind of ugly. But we're going to see that in the rest of the talk. The data are quite complicated and challenging. The data are all these scatter plots, and we included binary variables, we included categorical variables, and continuous variables. And so each of these little scatter plot is one of the problems, and you have to say, does A cause B, B cause A, or neither? The human eye doesn't do very well on this problem, although if you really, really concentrate, and after 10 minutes you get extremely tired, if you have only continuous variables, you can kind of guess, and you get a performance maybe 0.65 if you're really good at this. And the data set was created from both real data, where you had pairs of variables for which, with human expertise, we could determine with some degree of confidence that one was the cause of the other. For example, age and wages, city elevation, temperature, or in genomics, a transcription factor that triggers protein-induced. And in addition to that, we had lots of artificially generated data that were created by taking real variables but putting them through known functions. So we had truth value of the causal relationship. So we had 20% of the real data and 80% of the artificial data. And here are the results. So the scores are in AUC. And you see that performances are better for the artificial data than the real data, which probably are very noisy because it's human judgment, and it was very tedious to label the pairs of variables. And then we broke up the score into a dependency score, which is separating the pairs of independent variables from everything else. And for those, we have pretty good results. So it's easy to determine independence. A confounding score, in which we separate the pairs that are generated, that are actually dependent, but there is no causal relation between A and B. There is a third common cause to A and B. And if you separate that from everything else, you get relatively poorer scores. And then the causality score, where you separate A causes B from B causes A. So graphically, we can represent that and show here the top-ranking participants. So each point here is one of the participants, and we're showing their score on real data versus their score on artificial data. And we're showing the causality score, the confounding score, and the dependency score. So we are doing better at simple dependency. So these are the higher right corner point, the blue points. The hardest are the black spots, the confounding score, and the causality score kind of in between. But the very interesting thing are all the little crosses. All the little crosses represent the results that you obtain by random guessing. So by taking, by permuting randomly the target values and see whether we can make predictions for random guessing. And you see that the predictions that are obtained are very significantly better than chance. So how do we do that? Now, in the rest of my talk, I'm trying to give you an intuition how you proceed to build a causation coefficient and why the participants improved so much upon the state of the art. So everybody knows about correlation, and everybody knows that correlation doesn't mean causation, and also that you can have some variables that are dependent and have zero correlation, like at the bottom. So the zero correlation problem for dependent variables can be solved by independence tests. And if you do that, you move from a very poor performance to slightly better using tests involving, for example, mutual information or the Hilbert-Schmidt independence criterion. But that doesn't tell you how, from these scatter plots, you could determine causation. So here's one of the little artificial examples that I borrowed from Wikipedia. Here the input is a uniform distribution. The noise is also uniform distribution. And B is a function of A plus noise. So you can quite easily determine that these variables are dependent, even though they have zero correlation, using mutual information and this H6 test. Here, high mutual information indicates dependence, and a low value of I, which is the p-value of the independence test, means also strong dependence. Now, in order to determine the causal direction, what people did prior to the beginning of the challenge is that they did fit in two directions. So you can fit A as a function of B or B as a function of A. And if you have a good fit in one direction and a poor fit in the other, then you say, okay, I think I found the correct causal direction. And the second type of feature people very often use is to look at the residual. So the residual here is represented by the error bars of the fit. And if the residual is relatively constant throughout the curve, then it means that you probably have the right causal direction, because the residual is an estimate of your noise. And the noise is essentially another latent variable that you haven't measured. And so the noise is probably going to be constant if you are in the right causal direction. So people use these two criteria, the goodness of fit and then the independence between the input and the residual. So if the residual is constant, then it's considered to be a clue of the right causal direction. Now, unfortunately, these methods don't work always, because you have cases that are completely symmetric, like the linear case plus Gaussian noise, where you could generate the exact same scatter plot with A as a function of B, B as a function of A, or A and B generated by a third variable. So this is a so-called non-identifiable case. The good news, though, is that if you break one of these conditions, so if you go to nonlinear model, non-Gaussian input, or non-Gaussian noise, then you break the symmetry. And this is an example of a linearly generated example, but with uniform distribution for A and uniform distribution for the noise. And in that case, if you go through the same exercise as what I did before, you see that the fit is not the same in both directions. In the correct direction, then you have a residual that is constant, whereas in the bad direction, you have a residual that varies, and therefore is the independence test fails. So there is no independence between the residual and the input. So this is how you could detect the right causal direction. So this is where we were standing when we started this challenge. And after a few months of work of the participants, we were there. How did this happen? So typical research methods worked as follows. People restricted the domain of all possible cases to a subset of cases. For example, they considered only continuous variables, only non-Gaussian noise, only nonlinear cases with no noise, various cases like that. And then they studied a particular model, for example, the additive noise model, the post-nonlinear model, Gaussian processes. And finally, they came up with a test, and then they studied the identifiability, the consistency, et cetera, et cetera. But each paper that was published focused on just one restrictive aspect and one particular model, and came up with one test. What the participants did is that they considered the problem as a pattern recognition problem. Each scatter plot is like a little image, and how about extracting features from that image, and then once you have lots of features, apply a machine learning algorithm such as ensembles of decision trees, random forest or gradient tree boosting, and coming up with a big learning machine. That's where I said the solution's kind of ugly, right? Because it's much less easy to understand. Now you have a huge number of trees, hundreds of trees that are basing their decision on a very large number of features. And the features, however, they borrowed from all these papers that were published in the literature. So they consisted in independence tests, curve fitting results, and other features derived from the conditional distribution, information theoretic features, and some data statistics. So what I did is that I went back to these big forests that were built by the participants, and I tried to extract one simple kind of consensus tree using the most informative features. and with the purpose of trying to understand how these systems work. So using the results provided by the winner of the second phase and who also was second in the first phase, I came up with that tree. And at the top, there was a feature called Conditional Distribution Similarity that I had never heard of before. And then after that were differences in marginal entropy and maximum of the marginal entropies. So I went back to the paper and tried to figure out what is this conditional distribution similarity. What the authors did is that they conditioned on one variable after discretizing the variable. So they kind of binned the variable. And then they looked at the conditional distribution and observed whether the shape of the conditional distribution was constant while sweeping along the input direction. So this is kind of a generalization of this idea I mentioned before to look at whether the residual is constant. So it's trying to infer something about the noise that is something about this latent variable that we don't know of. And we want to know whether in one direction, the distribution, the conditional distribution, that is essentially the distribution of the latent variable, is more constant than in the other direction. And that would be indicating that we found the correct direction. So this actually is a true example of two variables. So A is the aspect, which is the orientation of a slope in a hill, and B is the hill shade at 3 p.m. And so we can play the same analysis as before, and we found there is a strong dependency between the variables. But when we do the fit, it actually doesn't work well. Amazingly enough, if you do a fit, the fit in the wrong direction has the smallest residual. And in both directions, you have a very strong dependency between the residual and the input variable. The reason is that you don't have an additive noise model here. You have actually a noise which is pretty multiplicative, or some more complex type of noise combination. So the additive noise model doesn't work. However, this idea of using the latent variable and the independence of the distribution of the independent variable with the input works still if instead of just using an additive noise model, you use the conditional distribution. And this is what I'm representing on this slide. The plots in the lower left corner here are representing the conditional distribution. And this CDS feature that was computed by the participants who provided this really profound model have an amazing difference in value here for this particular case, and allow us to discriminate between the two directions when in fact the additive noise model was failing. So what happens is that you can, by conditioning on variable A, you can find that the distribution here is in fact self-similar all across the spectrum. And once you have rescaled with respect to the span of the distribution. All right, so that's just to give you a flavor of what the participants have been doing. They have been creating, hundreds, and for the actually top-ranking participant was thousands of features automatically generated. There's much to do now to keep trying to understand what these features do. But the amazing thing is that challenges can help making big leap in data science. And they provide solutions that open up entirely new fields of research. Now that the new baseline is so high, the entire research community can set up to work on this problem and try to understand it better and analyze the features, derive theoretical results, and test on other data. So our next challenges will address causality in time series and entire network reconstructions, but we also have a lot of other types of challenges in the pipeline. And we also invite you to come and join the community of challenge organizers and put up your own challenges on the CodaLab platform. Evelyn is actually making a demo just after this session, if you follow us, to show you how you can post your own problems and have lots of participants contribute and make big leaps forward. Thank you for your attention.
Thank you, Isabelle.